Hello, everyone. This is John Munn with Interstate Stream Commission of New Mexico. We will give everybody a few more minutes to jump on, and we'll get this presentation started. All right, we'll get started. My name's John Munn. I'm the water planner with the Interstate Stream Commission of New Mexico. Today, the Interstate Stream Commission is presenting an in-depth webinar on the leap ahead analysis. Our subject today is impacts on hydrologic processes by Dr. Fred Phillips. Next slide, please. So for anybody that has been on one of these webinars in the past, I'm just going to go over some introduction slides on information to inform you of what the 50-year water plan is and future webinars coming up. If you've been on these before, I apologize, it's a repeat, but it's good for anybody that's new. So just go over the 50-year water plan, big picture of what we're doing. Again, we're seeking engagement of experts and stakeholder expertise from across the state of New Mexico. We want public input on this project. Our big goal is to build a science foundation. That's where our science experts with years and decades of research on climatic and water sciences to build us a leap ahead analysis assessment looking towards the 2070. And that's what our science foundation is for the 50-year water plan. The next piece would be the resiliency assessment, where we want to engage with the public, boots on the ground decision makers and experts on managing water and people that deal with water on a daily basis throughout the state on how resilient are you to these changes coming, and what can we do about that. And then the next step would be the adaptation strategies development, where we look at how we assessed our resiliency and we engage our public input, the boots on the ground experts, decision makers, and the scientists to talk about different adaptation strategies to deal with these changes as they're coming, and produce at the end recommendations on policy, operations, land management, local decision makers, and research. And so our big goal is to come up with recommendations at the back end from all the public input backed by a science foundation. Next slide. And this is just a little kind of update on where we're at. In August, we're working on webinars for all based on leap ahead analysis. Again, all the authors for chapters are giving in-depth webinar presentations so that you can look deeper into the leap ahead analysis. And then in September, we're going to initiate the resiliency assessment. We're going to have a resiliency information forum on September 1st. And the ISC will look at talking about resiliency. What is that? Where are you at in that concept? And start initiating that discussion in September. And during all of this, we want to do a continued parallel tribal and Pueblo outreach and communication. Next slide. And finally, we have the 50-year water plan has a website. At that location, there's a lot of information on the 50-year water plan. Also, the leap ahead analysis, there's links to look into videos and information videos to links to our partners and teams that are helping us through this process. We ask if you ever have questions or comments on the Leap Ahead analysis webinars or the Leap Ahead analysis once it's open for public comment, or the 50-year water plan and resiliency assessment process, please go to our public input comment page. It's all over the website. You'll find links and you can jump on there and make comments then and questions, and that way we're making sure that we're gathering that all in a data set and collecting that. If you have just a general quick question, if you get lost on the website or you haven't been receiving any of the newsletters from the water plan department, please shoot an email to the water plan email, and that way we can get you added to that. Also, for questions today, there is a questions box on your in the upper left-hand corner, I believe, of your screen. That's where you can drop it down, and if you have questions, feel free to submit them there throughout the presentation, and at the end we will answer those questions. And next, I'm introducing Dr. Fred Phillips for our presentation today.
Okay, so can everyone see the, John, I guess you're the only one who can answer. Can you see the slide correctly in slideshow mode?
It is, it's not on the full slideshow share, but I can see it. It's, okay. If you go down and probably hit that slideshow button.
Okay, whoops, let me go back. Okay, now can you see it?
Yeah, if you want to back up a slide, I think you're on your introduction slide.
There, is that correct?
Perfect. Yep.
Okay, right. Very good. Okay, so this is actually the third chapter of our Leap Ahead analysis report. The first one was an introductory chapter. The second one is on projections of climate change for New Mexico. And so the third chapter is a kind of a follow-on to that. It would have been more logically presented a little earlier in the series of webinars, but I was on travel at that time. So here we are trying to assess the effects of climate change on the land surface water budget. And that is really sort of at the heart and soul of effects of climate change on water resources. I'll step back to the chapter 2 presentation. This is a slide out of that presentation, and it sort of summarizes in one slide the projections for the future in New Mexico. So in the upper right here, just a second, I'm gonna get a little bit more visible. So here in the upper right, you have the historical record of temperature in New Mexico since 1900. And starting about 1970, we begin to see the temperature increase in line with models of what we would expect from global TCMs. And then in red and green, different emission scenarios for the future going to 2100. And regardless of which emission scenario you select, we have a steady increase in temperature for the next 100 years. Precipitation, in contrast, is much harder to predict. And so here on the lower left is the December-January annual precipitation average. And the present up to the present is in gray, and the future is in blue. And basically, we don't see a lot of change in the average of all of these GCM simulations, but there's quite wide bounds around what we might expect. And finally, on the lower right, we have the actual temperature and actual precipitation. In more detail, you can see that more or less linear increase in temperature on the top in red here. And then precipitation goes up and down. And since since this trend in temperature became really apparent, which is about 1995 or so, we see that precipitation appears to have decreased. But what the significance of that is a little harder to say. Just a second. My controls have disappeared here. Let me. Sorry,
Is it allowing you to go to the next slide?
It's frozen up is what's happened. Basically, I cannot advance and I cannot even get out of the screen. I'm going to stop the show here, okay, and go to PowerPoint and advance. No. It's a PowerPoint problem on my end. Okay, there we go.
There you
go. Okay, and it's in slideshow mode?
Yes.
Okay, sorry about that. PowerPoint on my computer occasionally just sort of freezes up. Okay, so I'm going to start out here with a point that we all know very, very well. New Mexico is an arid state. And this quantifies the aridity in terms of a parameter called the aridity index. And that index is simply the ratio of potential evapotranspiration to precipitation. And so here is the scale over here, and this bright red color is greater than 5. And we see that that means that the atmosphere could potentially evapotranspire 5 times as much precipitation as actually falls over the state. So the question we're interested in here is what's going to happen in the future. And for that, I have this map here, and that is a projection of what the aridity index is going to be over New Mexico specifically, not the whole US. And in, but you know, the average between 2040 and 2069. And so we see, this gives us a lot more detail. We see that the low elevation desert areas of New Mexico have aridity indexes that are somewhere between 6 and 10, very high. Whereas the areas that generate most of the runoff and also most of the groundwater recharge up here in the northern part of the state, the Sierra Blanca over in the Mogollon Mountains area, those are at much lower values, higher than 2. 1 is a pretty typical value, going up to as high as 0.5. The atmosphere can only evaporate half of the precipitation that falls. So you can see why those are the areas generating the runoff. So how does this map compare to the previous one? I don't unfortunately have a comparison at the state level, but here is one over the US. Here is the aridity index map I showed you before in the small image in the lower left. And the change in the aridity index is in this one. And this is, they had, this paper by Hydrological et al. Had projections for an arid sort of scenario, a moderate scenario, which means more or less precipitation similar to today, and a wetter scenario. So I picked the moderate scenario. And it shows the aridity index in New Mexico increasing by something like half an aridity index unit up to 1 or more aridity index units. So for example, if in a particular place the aridity index was 4, in 2080 it would be 5. So it's a significant increase in aridity. So how is that then going to translate to changes in water resources? Well, we have to keep in mind that the thing that I started out with my point, New Mexico is an arid state, or semi-arid in parts of it. So that means that two fluxes dominate the water budget: precipitation and evapotranspiration. And together they account for 97% of the hydrological flux. Interesting thought. And the parts of it that we can actually divert and use and so on only account for about 3% of the budget. So there's kind of a big lever arm here. Small changes in the two big terms can make a big change in the residual terms. So this is a more graphical expression of that water budget. The numbers that are on these flex arrows are millions of acre feet per year. So precipitation over the state is about 95 million acre feet per year. Transpiration 75, evaporation 17, and then runoff and recharge together only account for about 3.2 million acre feet per year. So let's just pose the question: suppose we increase transpiration by 1.5 million acre feet per year and we hold precipitation and evaporation constant. How is that going to affect the water budget? So I'll just digitally change it 75 to 76.5. Well, it has to come out of runoff and recharge since we're holding the other two constant. And so I just decrease them proportionately. That gives us 0.9 and 1.1 million acre feet for those. That may not seem like a big change, right? In terms of the absolute values here, it's not big at all, but proportionally it's huge. So we have increased transpiration by 2%. The result of that is a 40% decrease in runoff and recharge. So, small changes in the water budget driven by global climate change can potentially make big changes in the amount of water available. So what are the mechanisms that cause climate change to produce changes in runoff and recharge? First of all, we have the direct effect. Decreased precipitation is fairly obviously going to decrease runoff and recharge. And increased temperature will increase evapotranspiration, and that will decrease runoff and recharge. So that's just general principles. I have a graph here on the lower right that is a quantification of that. It's from a Budico type analysis from a recent paper by Yang et al. And the top in blue shows you the sensitivity of runoff to changes in precipitation. So a 1 millimeter increase in precipitation will cause, however much the line indicates, change in runoff. And this is really runoff and recharge lumped together in terms of this analysis. And on the bottom one, we have the same thing with evapotranspiration. So for example, if we are in a physically impossible situation where the aridity index is 0, i.e. there is no evapotranspiration, then if we have a 1 millimeter increase in precipitation, we'll get a 1 millimeter increase in runoff, okay? Conversely, if we are at a very low, very high value of the aridity index, like 5, the vast majority of the precipitation is being evapotranspired anyway, and a 1 millimeter increase or decrease is simply goes into that evaporative flux, evapotranspirative flux, and it doesn't change the amount of runoff very much at all. So for the areas that are hydrologically significant in New Mexico in terms of producing runoff and recharge, kind of an average value for the aridity index would be around 1. So that says if, for example, we had a 10 millimeter increase in precipitation, we would get something like a 6 or 7 millimeter increase in runoff. And if we had a 10 millimeter decrease in a 10 millimeter increase in potential ET, we would see something like a 3 or 4 millimeter decrease in runoff. So this sort of gives you an idea of the magnitude of the response that we can expect from changes in temperature and in evapotranspiration. But in addition to these direct effects, we also have indirect effects. And those include the effect of the seasonality of precipitation. So if we change the precipitation or the evapotranspiration in winter and spring, that's going to have a much bigger impact on the amount of runoff than changing the amount of precipitation in the summer and the fall. Another thing I'm going to sort of informally call the clumpiness of precipitation. So suppose we keep the amount of precipitation constant, we also keep evapotranspiration constant, but we change to having more frequent, smaller precipitation events that are spaced widely in time. We're going to get a decrease in runoff and recharge, even though we haven't changed the averages at all. Conversely, if we change to less frequent precipitation events that are larger and they're clumped together closely in time, we'll get a major increase in recharge or runoff, even without changing the average values. Okay, so these secondary effects are potentially as important as the primary ones at temperature and precipitation. But remember that while I showed you in those earlier graphs, temperature is pretty predictable. Our ability to predict precipitation is much less strong. And then the ability to predict things like seasonality and clumpiness is one step beyond that. So these are questions that we can potentially address, the secondary effects, but they're difficult to do at the present time with our present knowledge of what future climate might be like. So I'm going to focus on the primary effects, temperature and precipitation. Although, in fact, those secondary effects are potentially included in these models that I'm going to show you. So let's move to talking about approaches to predicting runoff and recharge. What are the methods by which we can do that? Well, the main one is numerical simulation, of course. And so the classical approach is used on that, and those are the large majority of things that I'm going to be showing you in this talk today are the result of using downscaled global circulation model simulations of the future as input to local scale land surface hydrological models. And so this diagram kind of symbolizes that. We see a global circulation model that has a very coarse resolution. This particular one in this illustration from a 2018 paper is 280 by 420 kilometer cells. So we're sort of starting to approach the scale of New Mexico itself with one cell. So we need to downscale that, and I'm not going to talk about that at all, to a much finer resolution. And in this example, it's 25 by 25 kilometers. In fact, if we're going to really look at things that are happening in New Mexico in any realistic detail, we need to be somewhere between a quarter and a tenth of that 25 kilometer scale. Then we use that downscaled metadata, not metadata, but virtual data to drive a hydrological model. And that's what this green third layer is here, hydrology, vegetation, topography. So that's our land surface hydrological model. And then finally on the bottom here, we can put that into a model that might include things like population growth or changes in technology or stuff like that. I'm not going to talk about that kind of thing at all. So what are the sources of uncertainty in this modeling approach? Well, the main one is human beings, right? What are humans going to do? Are we going to wake up and say, we really have to do something pretty significant to turn the situation around and fairly quickly convert to a carbon neutral economy? If we do that, we could end up on this representative concentration pathway 2.6 in blue, and maybe have something on the order of 1.5 degrees of global warming by the end of this century. On the other hand, if we shrug our shoulders and don't actually get the act together to do anything, we could be on the red line at the top, representative concentration pathway 8.5, which would result in something like 4 to 5 degrees temperature increase. So we have to make a selection, and typically we just choose one of these alternatives here. And usually the alternatives that are chosen are the 8.5 and the 4.5, representing a relatively optimistic scenario for the 4.5 and a pessimistic one for the 8.5. However, there's also a lot of uncertainty that comes out of the GCMs themselves. There's a lot of GCMs. This figure, that list of colored boxes on the bottom, are all of the different models that were compiled in this 2021 figure. And that's not all the ones that are available. And the black line in the middle of the figure is historical data. And so this is for the 20th century, and it shows, you know, the change of temperature in the USA over the 20th century, and it shows the modeled results. And the thing to take away from this figure is how broad the band is. If we go from the top to the bottom of the colored band, we are looking at something like 2.5 degrees of temperature difference. So remember that temperature is the most predictable parameter. So for something like precipitation, the band is even wider. So we have to somehow deal with this uncertainty that is inherent in the modeling process. It comes out of different models and different parameters, and then just different stochastic behavior of the system. So with that said, let's move on to the results from modeling studies in the New Mexico region. And I'm going to focus mainly on the Rio Grande and the Upper Colorado, which they're both within New Mexico, and they are the two very significant rivers or tributary rivers that we have to deal with here. So probably the most widely cited and used study is one by the Bureau of Reclamation for the Rio Grande. And this kind of summarizes their results from 3 different scenarios. They don't use the research was done before the RCP scenarios were developed. So these are the old A2, A1, etc. So A2 is the highest emission scenario, and B1 is the lowest emission. And they only present the median results here. They don't show you the envelope around them, although they do in other figures from their report. But this makes it pretty easy to digest. So what is the take-home message from this? If we are interested in 50 years in the future, that's about 2070, and the results suggest that average discharge of the Rio Grande at Ottawa will decline from about 1,500 cubic feet per second in the middle of the 20th century down to about 1,000, or a 30 to 40% decline in river flow. How about the Upper Colorado, a recent study by Udall and Overpeck? And we have these probability distributions for what is likely to happen. And so there's 2 scenarios, the 4.5 and the 8.5, and then they parameterize this by a response function type of thing, percent change in discharge per degree of warming. Assuming that these higher emission scenarios are the ones that's applicable, we are looking at, by mid-century, looking at something like 20 to 40% reduction in flow, and by the end of the century, something like 30 to 50% reduction in flow. So the results are pretty similar to what the Bureau of Reclamation study got for the Rio Grande. Although you can see that they used a independent type of uncertainty analysis, which narrows it a lot, but even so, the uncertainties for their various scenarios are pretty broad. And here's a third one. And this is from the National Climate Assessment Report for 2013. And it compares annual runoff in, say, 2050 or 60 versus the last 3 decades of the 20th century. And if you look at the color scale here for northern New Mexico, the area of the Rio Grande, and then the Gila Mountains and so on, you're looking at something like 20 to 40% change in runoff based on that. So again, pretty similar to the other 2 studies that I just showed you. However, let me throw in a fourth one that gives you quite a different result. This is a study by Elias et al., 2015, of just the upper Rio Grande, and it used a specialized snowmelt runoff model to do this, as opposed to the other ones that were done with the VIC. Well, yeah, they were done with the VIC model, which is a standard way of interpreting the climate model outputs. And here, I'll warn you first that the blue color here is just the outline of the basin. The color is not actually corresponding to anything in the index over here, the key. And the numbers are the numbers of the basin names. It has nothing to do with the percent change. So you just have to look at the colors. So they tried to kind of bound the estimates. They took all of the various GCM studies and they grouped them into 4 categories: warmer, wetter, warmer, drier, hotter, wetter, hotter, drier. And then they ran their model for all of them. And here we get a really big range in the change in runoff. So they get around minus 25% for their warmer or hotter, drier models. However, for the warmer, wetter ones, they go up to plus 50% increase in runoff. And this, you know, that's to a first order, that's a reflection of that really wide grouping of model outputs that I showed you in an earlier slide. So if you just want to accept that and sort of crunch through the numbers, you end up with something like this. And the problem is, I don't think that that is very useful to most of the people who are trying to do water planning, saying, well, you know, in 50 years, you could have 25% less water, or you could have 50% more water. That's no better than saying, throwing up your hands and saying, we have no idea what's going to happen, is it? So how are we going to deal with this kind of uncertainty? To help answer that question, I'm going to move on to my next topic, which is historical analysis of runoff trends. And this is a plot from one of John Fleck's publications of the discharge of the Rio Grande at Albuquerque. And I've highlighted, it goes from 1940 to 2017 or something like that. And up here at the top, I've highlighted the period where the signal of global warming temperature-wise is unambiguous. And so one can do just a quick scan of this plot, and you know, the height of the bars, the horizontal line is the average, and say, wow, if I look at that data, the bars that are under the red bracket there, they sure appear to average lower than that brown line in the middle. And in fact, they do quite a bit lower. But what is the significance of that? Is that due to the effect of global warming, or is it due to something else? And in order to, so there's a kind of trend that I just drew by eye through that data. Looks like it's going down a lot. To answer that question, we need to consider the role of atmospheric teleconnection on runoff trends in the Southwest. And a lot of research has demonstrated that the principal control is the Pacific decadal oscillation. And this graphic shows you how that works. These are sea surface temperature anomalies. So when the PDO is positive, you have a pool of cold water up in the North Pacific and hot water relatively speaking, in the South Pacific. I mean, it is hotter there too, but these are anomalies. And then in the negative phase, you have a warm water in the North Pacific and cooler water along the equator. So those are the two phases of the PDO. It turns out they have a big effect on the amount of precipitation in New Mexico and the Southwest. So on the bottom, let's focus on the bottom for the moment. This is the PDO index with the warm phase here in red, bars going up on the top, and the cool phase, bars going down in the blue below the line in the middle, the zero line. Okay, so you can see that these periods of Pacific Decadal Oscillation are not randomly scattered. They are grouped together quite coherently. Up here, I have highlighted the bars in the discharge of the Rio Grande graph in the same way. And all it takes is a glance between the two to say, wow, yeah, there's really a correspondence. So here from about 1950 to 1975, we have almost all blue and just a couple of red. Here we have almost all blue, and there's more red, but there's still not very many. Note here in particular, there's 2 years that have a warm regime in the middle of this cool one, and those are big runoff years in the Rio Grande in the middle of the 50s drought. Okay, then we get up to 1975 to 98, and it's almost all red bars in the PDO graph, and it's almost all red bars up here. So, you know, there's a strong correspondence between the PDO and the amount of precipitation. The important point is, for the past 20 years, when global warming has been unambiguous, we have mostly blue bars. So that means that we would expect less precipitation, less precipitation, but less runoff in the Rio Grande anyway, even if global warming were to happen. And so that confuses the situation with trying to tangle out effects of global warming from effects of teleconnections. But with that said, let's look at some of the historical trends. So the top one is from Xiao et al. And it shows the discharge of the Upper Colorado River, a naturalized flow of the Upper Colorado in blue. And you see that there is a trend of about minus 3.3 cubic kilometers of water per year from the drainage basin over the period from 1920 to the present. If we look at the part since global warming became clear about 2000 or so, we see that that is low, right? The mean is definitely lower than the mean for earlier periods. But to what extent that is part of some long-term trend that is independent of global warming, and to what extent it is due to the PDO, and to what extent it is due to global warming, we can't really sort out. But there is one thing we can pull out of this, and that is if somebody wants to say global warming is going to produce a big increase in runoff in the Southwest, we can say the data sure don't seem consistent with that. Okay, let's look at the annual runoff of the upper Rio Grande, and that's this graph down here. Note that the time scale is different, 1955 to 2015. Here we don't have really any kind of long-term trend. It looks relatively stationary, stable, right? But once again, for the period from about 2000 up to the present, it's low, right? The average is lower than the average for earlier periods. It's hard to disentangle what the reason for that is, but once again, we can say it certainly does not support a scenario of increasing runoff in the Southwest with warmer temperatures. So that's the studies I'm going to show you on changes in runoff due to global warming. Next, let's look at groundwater recharge, and there's far fewer studies on that. I had to really pull out pretty much everything that was available, everything that had been done, because there's not much. So this is a global study done by Dahl et al. And using a model called water gap GHM. And This is one small section of their results, but it's pretty typical of the rest of it, and it's quite interesting. The colors indicate change of groundwater recharge in percent, with reduction in red and increase in blue. If we look at the area of New Mexico, which is right in here, it's all blue, right? It's hard to tell at this scale. It may be light blue, it may be dark blue, but that would indicate something like 50 to 100% increase in groundwater recharge. That seems contrary to the other evidence that we've seen. Why would we have low runoff if we're going to have an increase in groundwater recharge at the end of the century? So, going to put a question mark here. A study that is really probably a lot more useful for our purposes is this one by Narula et al. Quite carefully conducted study that focused specifically on the Western United States. It used the VIC model as well. So this summarizes their results. You can see New Mexico down here, and in the more arid parts of the state, there's a relatively small change in recharge on the order of maybe 3 to 5%. But in the higher elevation areas that have more precipitation and more runoff, we see a much bigger reduction, something like 15 to 20% reduction according to their modeling. This is more in line with the results that we saw for the projections of runoff. Soil moisture should be strongly correlated with groundwater recharge. It would be very surprising to have reduced soil moisture, but at the same time increased groundwater recharge. So it's worthwhile looking at projections of soil moisture as well. And what we see here, this is from the US Global Change Research Program report, so it should be pretty definitive. It shows changes in soil moisture by season. What we see are strong reductions in soil moisture for winter and spring, and then reductions, but less strong for summer and fall. So this assessment indicates fairly drastic drying of soils. How does that compare with the historical record? This paper by Deng et al., quite recent, did exactly that. They used climate records to reconstruct changes in soil moisture from 1979 to 2019. And so the orange red colors here are reductions in soil moisture, and we see that the area of New Mexico is toward the upper end of the reduction scale. And if you convert that, that would indicate a 10 to 20% reduction in soil moisture over the past 40 years. So that is consistent with reducing groundwater recharge, not with increasing it. We can also look at analysis of water storage trends using gravity methods. So this is a paper by Scanlon et al. 2015 looking at the upper Colorado River Basin. The gravity trends from the GRACE satellite are in pink in the upper diagram. And you can see that there's a pretty steady downward trend in that. They also used a modeling approach to compute soil moisture storage. That's in green in the bottom graph, and that shows a similar result. Now again, should we attribute that reduction to global climate change, or should we attribute it to the shift in the PDO? It's hard to say, but whatever we want to attribute it to, it's really hard to say that we're having increased water storage. We are clearly not. So let's sum up the future projections here. Detailed local studies project 20 to 40% reductions in surface water flow over the next 50 years, if you look at the median. However, if you try to use some fairly generous method of putting bounds on it, you can get results that are as high as a 50% increase in runoff. So that's a problem. We have to deal with that somehow. Is that realistic or is it not? Studies on groundwater recharge are fewer, but they mostly yield similar results. However, the reductions seem to be somewhat smaller than those for runoff, more like 10 to 20% rather than 20 to 40%. The historical trends of runoff and recharge over the period of clearly observable global warming are generally negative. It's difficult to know what we should attribute that to because there's strong influences on the decadal timescale in addition to warming, teleconnections. However, one thing we can definitively say is that the historical records provide no support at all for any significant increase in precipitation, runoff, recharge, or soil moisture. So this historical analysis does not support projections that include significantly enhanced precipitation and thus enhanced runoff, enhanced recharge over the next 50 years. It pretty much rules them out. I wouldn't say it rules them out, but it argues very strongly against them. So my conclusion would be that we should expect reductions in surface water flows and groundwater recharge that are in the range of 10% to 40% over the next 50 years. And the largest reductions are going to happen in the areas currently producing the most runoff and recharge. Finally, I'll end up here talking about knowledge gaps. The first knowledge gap that I'll identify is adequate groundwater storage and soil moisture data to guide future water resources projections. We're in a kind of a unique situation here. When we started out on this whole thing, if we'd done the same exercise we're doing now back in the 1990s, we would have to rely entirely on the numerical models, the GCMs and all that comes out of that. And which model was the best model, we just have to say nobody knows, right? We don't have any way to establish that. That's no longer true. We have 20 to 30 years of data that are during steady global warming. So a model that says that we're going to have 50% more precipitation in the Southwest over the past 30 years is clearly inaccurate now, right? It didn't yield the right prediction. There's no real reason to think it's going to yield the right prediction 50 years in the future. So we can use the knowledge of processes that are going on during global warming now to sort out those simulations and try to select the ones that are going to be the most accurate for the future. Okay, but to do that, we need data, right? It's not just good enough to say an average value for the globe or something like that. We need data from New Mexico. And so we need to monitor groundwater levels. We monitor groundwater levels in Albuquerque and in the Ogallala Aquifer and so on, where we're pumping like crazy. But in order to get at changes in recharge, we need to monitor groundwater levels in relatively remote areas. And there's a little bit of data like that, but there's not much. We also need to monitor soil moisture using technology like the Cosmos network that uses cosmic ray neutrons to get at soil moisture. And also fixed GPS stations can help us to understand changes in water storage. And those are critical for projecting into the future. A second knowledge gap is we need to establish sound criteria for post-processing global circulation model simulations that we use to drive our local simulations. We need to have an intellectual framework that will enable us to say, we're going to use this GCM simulation and not that one for sound, statistically and scientifically defensible criteria. Once we do that, we'll have a much more narrow range of outputs, and it will be much more useful for water resources planning purposes. Finally, we need to select or develop a New Mexico specific land surface hydrology model. There's dozens of them out there, and which one is the one that's right for New Mexico? Many of these models aren't suitable for our range of hydroclimate. They were developed for Europe, or they were developed for the Amazon. They're not likely to work real well here. So we need to sort out which ones reflect the physical processes in our environment. They also vary greatly in computational requirements, complexity, and level of expertise. So it would be nice to have a really simple model that would give us the answers we need. Maybe that's possible. On the other hand, maybe we need a really complex model, and we need to get the people to run it and make use of it. However, the bottom line is that if New Mexico wants to produce projections of water resources and environment that are useful for planning purposes, it should thoroughly evaluate existing models and either select one or commission one that can be used with confidence in our area. And with that, I'll conclude and I'll take questions. Thank you very much.
Thank you so much for this presentation. It was excellent. I will, again, please use the question box. It should be on top of your screen to send in questions. I will start with our first one. In the Colorado River and Rio Grande Basin modelings, how was the impact of large reservoirs handled in runoff estimates, reservoirs, impact downstream flows, etc.?
Okay, I will first of all confess that I cannot answer that question with any real confidence. They did include effects of infrastructure, I guess you would say broadly put, but I am not really conversant with the details of how that was handled in that particular modeling project. I see that Bruce is on the line here. Bruce, do you have a better answer than that?
Nope, I sure do not.
Okay. I apologize for not being able to answer it off the top of my head. On the other hand, I'll say that report is readily available for download, and it's quite a thorough report. So I am sure that the answer to that question is in the report.
Excellent, thank you. If vegetation cover is going to change negatively due to climate change, wouldn't the evapotranspiration change? Will this impact the runoff characteristics?
The short answer is yes. Okay. So we're there. We got in this question is getting into a level of complexity that is well beyond anything that I tried to deal with in this talk. But the answer is yes. That's what we call coupled processes, right? So climate affects vegetation, and vegetation in turn affects hydrology, and then the hydrology in turn affects the vegetation. So they're all coupled together. But if we are having wholesale changes in vegetation, which in fact that's not a hypothetical, that is happening as we speak. It's happening mainly in the higher elevation areas. I'll just step back from the question for a second here and say one of the interesting aspects of this as you look it over is that the areas that are most insulated from the effects of climate change are the low elevation deserts. They are in fact going to change very little, some, but not a whole lot. Whereas the high elevation areas that generate the runoff and generate the recharge are the ones where we are going to have wholesale vegetation change, and that will undoubtedly significantly impact runoff and recharge. But that's it's a very non-linear thing, and I'm not going to try and give a short answer as to how those changes might affect it. But for any really serious evaluation of water resources on a 50-year time scale, we need to take that into account.
Thank you. How will a 20 to 40% reduction in surface water flow affect rivers, their health, function, processes, including floodplains and riparian habitat?
That's a very, I mean, the answer to that question is very complex, right? And it depends partly on the nature of the river itself. So if it's a high elevation stream that is unregulated, it could have fairly, it could have, I think, significant impacts in terms of things like floodplain geomorphology, streamside vegetation, and so on. My gut feeling, without any, studies to back it up, is that on the Rio Grande, in fact, the regulated portion of the Rio Grande, let's say below Cochiti Dam, it's going to actually probably be fairly minimal. I think most of the geomorphic effects that we see happening are due to flood processes. They're due to high water from extreme events. And even if average flows decrease, extreme events may increase. And the flows themselves are completely regulated, right? They're other than intense storm inflows. Everything on the Rio Grande is due to people opening and shutting valves here and there. And so in that regard, it's probably not going to make a whole lot of difference, except that when they open up the valves, they're going to be opening them a lot less.
Thank you. Would the percentages, oh, I apologize. The question box jumped on me. Would the percentages for the Rio Grande be similar for the Pecos River?
I would think so. The Rio Grande Bureau of Reclamation study obviously didn't deal with the Pecos. They did deal with tributaries of the Rio Grande in New Mexico, and those behave similarly to the results that I showed you. So I would anticipate, given that the Pecos drainage basin is pretty similar to the drainage basins of tributaries of the Rio Grande in New Mexico, I would anticipate that the response would be similar. Although, let me add one thing, which is that there's a big difference between the modeled response of the Rio Grande at Del Norte, which shows a much less strong influence of climate change, than the modeled response of the Rio Grande at Ottawa. And the reason for that is, in large part, the human processes that are going on in the San Luis Valley, where water is heavily used for irrigation. And so that would not be a factor on the Pecos, which does not have that transborder aspect to it.
Thank you. Agricultural transition from annual crops to tree crops, pecan trees, etc. Will this have a significant positive or negative impact on evapotranspiration?
I am sure that, I mean, first of all, let me say that was outside of the scope of the chapter that I just presented here. This chapter is dealing with sort of changes in the hydrological system as a result of climate change across the landscape, and in very considerable part, looking at runoff and recharge generation. We did not at all in this chapter treat agricultural systems, and those are treated in another chapter by Phil King. I can't remember the number of it. And were Phil King presenting his chapter, he would be able to answer that question right off the bat. I cannot.
And Dr. King will be presenting on that next Thursday. That's when that will be talked about.
So show up at that talk and ask him the same question.
There you go.
And tell him Phillips said he could answer it.
Yeah, exactly. Great. What is your criteria for an acceptable New Mexico specific hydrology model? How does an investment in such a model pay for itself if hydrology is not the main source of future uncertainty? It seems like we need to embrace planning under uncertainty rather than spending extensive time and money to find one perfect hydrology model.
A very pointed question there. First of all, let me say that in comparison to the amounts of money that are going to be spent to adapt to climate change in terms of things like infrastructure and changes in legal systems. We're going to have changes in the way that we deal with our water allocations in a legal sense because of all this. Those are expensive. Lawyers are expensive, and so on. The amount of money that would be spent on a modeling exercise, the level I'm talking about here is minuscule. It is pocket change. So I'm not particularly worried about the cost of it. The effectiveness of it is another question. Well, let me just put it this way. Yes, we have to deal with planning under uncertainty. That's always the case, and it's much more the case with global climate change. But the more we can reduce and narrow those uncertainties, the more we can focus our responses. So again, if we're talking about real expenses in terms of infrastructure and let's say reductions in the amount of farming and stuff like that, loss of income from places that are no longer farmed, having better predictions will save us, a small amount of money spent coming up with a better understanding of what's going to happen in the future will save us real amounts of money when that future actually arrives. And while part of the uncertainty is due to the uncertainty in GCM outputs, a significant part of it is due to uncertainty in the hydrological models. And I didn't really go into that at all because, in considerable part because of time. But that's also a very significant factor. So if we can arrive at a model, it doesn't have to be one model. We could have a family of models, right? If that's considered to be the optimal solution. But I do think that having a appropriate model will help significantly to reduce uncertainties in future projections of water supply.
Thank you. We are out of questions. Is there anything that you or Dr. Thompson want to address to see? We'll give people a few more minutes if they have any final questions, but is there anything that you, from the questions that are being produced, anything else to cover?
I don't really have anything to add, no. Bruce?
No, Fred, and I appreciate the opportunity to comment. I think you've done a very nice job. There's a lot of uncertainty, and but the arrows are all trending or they're pointing in the same direction. That it's going to be drier, and it's going to be a challenge to figure out how to manage those resources.
Well, I want to thank both of you for the last few presentations, especially Dr. Thompson, but Dr. Phillips, thanks for the presentation today. Oh, we have one more actually, and this will be our final question. Do these models take into consideration the snow line going higher?
The answer is, well, by these models, there's a very, very broad range of models, and some very simplistic models would not explicitly deal with that. Those are not ones that one would seriously think of using for projection purposes, so I'm just going to rule them out and say that any model that one would think of using for serious projection and planning purposes would certainly involve the physical processes, right, that control the level of the snow line. And in the model, you should see it has to include snow hydrology, right? That's one of the things that, in spite of the fact that we're largely a desert state, snow hydrology is critical to runoff and recharge. So any model we want to think about seriously using has to include snow hydrology. And if it correctly incorporates the driving climatic parameters, you should see the snow line go up as temperature increases.
Excellent. Thanks for answering that final question. I want to thank you again from Interstate Stream Commission and myself for participating in the leap ahead analysis and this presentation. I really appreciate all the time you've put into this, and thanks for giving this presentation. Just for everybody, again, if you have any future questions that we didn't get to or comments, feel free to jump onto the 50-year water plan website. Again, there's links to the actual leap ahead, the climate and water advisory team's website also from there. It also has an event calendar and other spots, and also the public input page. Again, there's the event calendar. The next webinar is on August 26th at 2 p.m. It will be Dr. King, and he'll be presenting on surface and groundwater. And feel free to come and register for that. And we hope to see you all there. Thank you again, Dr. Phillips and Dr. Thompson.
You're very welcome.